Hello everyone, I'm Varsha from SVCE Computer Science Department. In this video, we will be discussing about joint probability and Markov chain. Introduction to joint probability distribution. Joint probability distribution is a fundamental concept in probability theory used to describe the probabilities of two or more random variables occurring simultaneously. It provides insight into the relationships between different variables and is widely used in statistical analysis and modeling. Definition of properties of joint probability distribution. Multivariate probability distribution. Joint probability distribution defines the likelihood of multiple variables co-occurring, enabling analysis of complex interdependencies and correlation. Probability density functions. It involves understanding the joint probabilities through functions that describe the likelihood of various outcomes, providing valuable insights into the overall distribution. Properties of properties and characteristics. Exploring properties like independence, covariance, and correlation provides a deeper understanding of how variables interact within a joint probability distribution. Calculation of marginal probability distribution. Marginalization. Calculating marginal probabilities from joint distributions involves integrating over unwanted variables, providing essential insights into individual variable behavior. Summation rules. Understanding the rules for summing probabilities across different variable configuration forms the basis for obtaining marginal probability distribution. Numeral methods. Advanced computational techniques can be employed to compute marginal probabilities in complex multivariate settings, ensuring accurate and efficient analysis. Next one, conditional probability distribution and its application. Conditional probability definition. Conditional probability expresses the likelihood of an event given that another event has occurred, offering valuable insights into cause-effect relationships between variables. Bayesian interference. It plays a crucial role in Bayesian statistics, facilitating the update of beliefs based on new evidence and making it applicable in diverse real-world scenarios. Third one, decision making. Conditional probability assists in rational decision making by incorporating past information to guide future choices, contributing to applications in fields such as finance and engineering. Coming to the Markov chains, Markov chains model sequential processes where the future state depends only on the current state, making them valuable for analyzing dynamic systems. Memoryless property. The memoryless property of Markov chain, where transitions are independent of the past, forms the foundation for applications in various fields such as physics and economics. Stationary distribution. Understanding the concepts of stationary distribution in Markov chains provides key insights into long-term behavior and equilibrium probabilities within dynamic systems. Definition and properties of Markov chain. Markov chains are characterized by transition probabilities dictating the likelihood of moving from one state to another, forming the building blocks of the chain. Irreducibility. Irreducible Markov chain ensure that every state can be reached from any other state, reflecting the interconnectedness and persistence of the system. Periodicity. Understanding the periodicity of Markov chains aids in discerning recurring patterns and rhythms within the state transitions, contributing to diverse modeling applications. Transition probability matrix and stationary distribution. Transition matrix encapsulates the probabilities of moving from one state to another, forming a fundamental representation of chain's dynamics. Stationary state. Studying the stationary distribution provides insights into the long-term behavior of Markov chain, characterizing the stable state probabilities under repeated transition. Convergence analysis. Analyzing the convergence of Markov chains towards stationary distributions offers valuable information about the system's behavior over time and its equilibrium states. Markov chain convergence and limiting behavior. Limits and stability. Studying the convergence properties and limiting behavior of Markov chain aids in understanding the long-term stability and predictability of dynamic systems, informing decision-making processes. Ergodicity. Ergodic Markov chain exhibit properties of long-term mixing and exploration, contributing to their utility in modeling diverse phenomena with complex dynamical behavior. Regenerative process. Chains with regenerative properties enable the study of renewal processes and cyclic behavior, providing insights into systems with periodic patterns and recurring events. We can find applications of Markov chains in various fields like biological sciences, financial modeling, and engineering systems. In biological sciences, we find application in modeling genetic processes, ecological dynamics, and population studies, aiding in the analysis of complex biological systems. In financial modeling, they are used to stimulate market movements, assess risk in investment portfolios, and model economic processes, providing insights into diverse financial scenarios. Under engineering systems, Markov chains are applied for reliability analysis, quality control, and modeling dynamic system behaviors, contributing to the development and optimization of engineering systems. So, to conclude this topic, the key concepts we explored: reflect on the fundamental concepts of joint probability distribution and Markov chains, emphasizing their significance in analyzing complex probabilistic scenarios and dynamic systems. Real world relevance. Highlight the practical applications of these concepts in diverse fields, showcasing their utility in solving real world problems and supporting decision making processes. Future exploration. Encourage further exploration of advanced topics in probability theory and stochastic processes, fostering a deeper understanding of probabilistic modeling and its application. So, this was it for the topic. Thank you.